Okay, this lecture is going to be about traffic signals. We have already discussed a few things about traffic signals, mainly their types. So now we are going to go further into this topic. Let me just bring on the. Okay, so first of all, some guidelines if you are going with the traffic signals. Once the signal installed, it must remain operational at all times, so you cannot switch it off. And the other thing is, with the signal, you cannot use any other traffic sign. For example, a stop sign or a give way sign cannot be used with the signal. Both these guidelines are related to avoiding confusion for the drivers. So, for example, if the signal has already been installed, so the drivers, when they are approaching the intersection, they are expecting to go through the intersection as per the indication of the signal, and certainly they find the signal uh, to be off. Then it will be confusing for them. What should they do? Is it only off for them, or is it just a problem with one light, or what? Another, the second guideline is again to avoid confusion for the drivers. So, for example, you have a stop sign and there's a signal. So, what to do if the signal is green and you still have the stop sign there? So, this can create confusion. There is an alternate. If the signal is not working properly, then the alternate is you keep the signal in a flashing mode. So it keeps on flashing a particular light, yellow or red, and that indicates to the driver that signal is not working properly or is not operational, fully operational, and then he can move according to his or her own judgment. What are the benefits of having a traffic signal? Because signal requires more maintenance, obviously it requires certain installation operations, and then you have to maintain the wiring and the lights and everything. So why should we do this? The first thing is the capacity. Among all the traffic control devices which are installed on an intersection, signals provide higher capacity than any one of them. Secondly, signals avoid most of the severe crashes, because these crashes involve, head-on collisions or right-angle collisions. So these are very severe crashes, and because of the signal timings, vehicles which are in conflicting directions do not or are not supposed to enter the intersection at the same time. So these types of crashes are reduced. You may see other types of crashes still happening on the or near the intersection. For example, side swipes because of lane changing, or rear end crashes, but they are not because of the signals. They are because of judgment of the drivers. So, and they are considered less severe. So there's it's a less critical issue. Installation of a signal can provide you a continuous movement throughout the arterial when the intersections are close to each other. So you have three, four intersections which are close to each other. If you keep them unsignalized, then you cannot control where the drivers are stopping and when they are stopping. But with a signal, you can actually program the series of signals in a way that one driver stops at the first signal, but then when he reaches to the next intersection, he finds the signal green. And then when he reaches the next intersection, he still finds it green, and so on and so forth. So you control the timing, and then you allow the drivers to go through continuously without stoppage. The last thing is for the minor movements. So you may have pedestrian crossing the major road, or you have cars coming or vehicles coming from the minor road. Unsignalized intersections, then they take or they don't provide enough opportunities for these minor movements to enter the intersection, because especially in the peak hours, because the movement from the major road is continuous, so it's happening, okay, continuously, so there's no chance for the minor movements to enter. But with the signal, even in the peak hour, when there's no gap in the traffic on the major road, the signal will force stop them, so it provides the chance to the minor movements to cross as well. Signal indications, we know about green, yellow, and red. They are called balls because of the shape of the signal lights. They are circular, so we call them balls. uh, Yellow ball or yellow light, we are discussing about the most critical one, which is the one where signal goes from green to red. And it is more critical because the vehicles are in the moving position. They are moving, so it's more critical then because then the accidents can happen. In Bahrain, we adopt the yellow after red as well, but since the vehicles are stopped, so it's not really dangerous. But as far as the timing is concerned, you can calculate the timing for the yellow, which is between green and red, and you can provide the same timing for the other yellow as well. There's no issue with that. Then I already mentioned flashing yellow and flashing red. So it is used, or there this mode is used when the signal is not operational or fully operational. It indicates a warning to the driver, and obviously, yellow warning or yellow flashing is less of a warning or represents less of a danger as compared to flashing red. Then we have error indications, which are in the signal, and they indicate that the phases of the signal are separated for different movements. So you may have a different phase for left turning or right turning or something like this. Sight distances for signals, they are according to the speed of the road, and we take 85th percentile, as I've already explained in one of the earlier chapters. And as the speed increases, the sight distance also needs to be increased so the drivers have more time to react to the signal components, uh, in the sense that they are the important values for the signals. Okay, so they are not the physical components, the pole or the lights. Then we are not talking about that. Okay, so we have a signal cycle, which is which goes from starts from red until the start of the next red. The time which is taken by the cycle is called cycle length. In one cycle, you have intervals, and each interval represents the time when the signal lights are a particular signal light is on. So when the green light is on, we call it green interval. When the red light is on, we call it red interval, and so on and so forth. Yellow, when the yellow light is on, we can call it yellow interval or change interval. So both of them are the names given to yellow time. Then we have a time which is called all red or clearance interval. This is the interval when signal just goes from yellow to red for one approach, but it doesn't go from red to green for the other approach immediately. It takes a little bit of time, and that time is given for the vehicles which are already in the intersection from the previous approach, and this time is given for them to clear. So the whenever the signal becomes red for one approach, the next approach doesn't receive the red immediately. It takes a little bit of time, and that time is called as clearance interval or all red, because in that time all approaches have red. Then we have the phase. Phase is again part of a cycle, and phase consists of three intervals: green, yellow, and all red. In these three intervals, one approach is allowed to move, or vehicles from one approach are allowed to move. Okay. Uh, in all red, you may argue that in all red, that approach has red, but the vehicles which are in the intersection are already from that approach. So the clearance or the all red time is still for them. So phase is the total time given for the movement of one approach. Okay, we can operate the signal in a pre-timed manner, semi-actuated manner, or fully actuated manner. Pre-timed means that the signal timings are fixed as per the expectation of the traffic engineers. And then we have a signal programmer, which is given this data, and he programs the signal timing according to the expected traffic. And we know that traffic pattern changes throughout the day. So pre-timed operations require different timings to be programmed in the signal according to different times of the day, because in those timings the traffic pattern is changing. So we may have one direction which is very heavy in the AM peak, and another direction which is very heavy in the PM peak. So signal timings will be different, but they are fixed. Then we have semi-actuated, which is used at the intersection of a major road and a minor road. And we have a sensor on the minor road. And this, because of this sensor, we call the signal as semi-actuated. And this sensor will collect the data of any car which is approaching from the minor road. And if there's a car, the signal will give the green time to the minor road. Otherwise, the major road receives continuous green. So the semi-actuated operation makes sure that the minor road receives the time whenever it is required. Then we have fully actuated operation in which sensors are installed in all directions. It is applied at the intersection of two major roads, and the idea is that the traffic changes or can change in any direction, so signal should change its timing according to that. So obviously, when you're changing all directions, then cycle time is also changing. Okay, all intervals are changing, and even the sequence can change. Okay, so it's not like after east always you will have the next green for the west. It may be for north for one cycle, maybe south in another cycle, depending upon traffic. So all these things are changeable in fully actuated operation. So the word actuation refers to connection with the sensor. Then we have signal coordination, which I already mentioned earlier. It is applied on a major road to have continuous movement of vehicles through a series of intersections, which could be less than zero point 0.5 miles from each other. All of them are signalized, and then you try to make sure that when vehicles are going from one approach to the other approach, from one intersection to the other intersection, they don't receive red again. So how we do it? We calculate the time which the vehicle is expected to take from one intersection to the next intersection. We call that time as offset, and then we make sure that the next green happens after this much offset. How do we calculate the offset? We know, or we estimate the average speed of the road, and then we divide by the length to get the we divide the distance by the speed to get the time, the offset. Okay, and for coordinated signals, the cycle length must remain the same for all the signals, otherwise it's not possible to do the coordination. In wherein we have some highways which I mentioned here, which have the coordinated operations, but coordination works if the vehicles are moving according to the speed which you have estimated. Sometimes vehicles are too slow because of traffic. Sometimes there's already a very long queue. So obviously in those cases, coordination doesn't matter then because you're already stuck. So in some cases, the road is completely empty and the vehicles come at, you know, bullet speed. So again, they will stop because they are faster than what we have expected. Okay, then we have the concept of saturation headway and saturation flow rate. Saturation headway is measured at the stop line of the signal, and it is the minimum value of the headway between the vehicles. And saturation flow rate is the maximum flow rate which you can have at the signal. It's an imaginary value because it doesn't take into account the stopping or any lost time or any delay at the intersection. Okay, so it's an imaginary value. So highest flow rate is saturation flow rate, and minimum headway is saturation headway, and the relationship between them is given here. There is saturation headway, and divide by 3600 for the hour, it will give you saturation flow rate. How do I measure saturation headway? So you go to the intersection and you start measuring the headway between the vehicles. Now we know the first 3-4 vehicles, their headway will be higher because their speed is slower, and they may have taken some time to get started. Okay, because they just saw the signal becoming green. So when they crossed the stop line, they were slower and had more gaps between them. So this is not the saturation headway. Saturation headway starts occurring from the third or the fourth vehicle onwards. So you ignore the first 3-4 vehicles in the queue, and then you start measuring the headway, and that is called as saturation headway. And then you do it a number of times, and then you get the average value. That average is taken as saturation headway. So you can see the graph over here. So for the first headway is higher, then it keeps on getting lower and lower, and reaches here the minimum constant value, and we call it this as a saturation headway. And then from saturation headway, you can calculate saturation flow rate. Now you can see the first 3-4 vehicles, as I already mentioned, that they have taken some extra time, and that extra time is called as startup loss time. So there's some startup loss time for the first headway, second headway, third headway. So you add all of them together, you get the total startup loss time, L1. And then you have another loss time, which is called as L2, which is the clearance loss time. It is mostly the all red time, which I already mentioned earlier, but it could be some part of yellow as well. Okay, which I will come back to it later on. But for now, let us say that this is the clearance loss time when the signal is all red. Okay, then we have an effective green time. Effective green time is phase time minus loss time. Okay, so what is a phase? Again, green, yellow, and all red. So this capital Y represents yellow and all red. Okay, small y represents only yellow. So you need to keep it in mind. Okay, so green, yellow, and all red minus the loss time. Again, loss time has two components: startup loss time and clearance loss time, which I already mentioned. So from phase time, if you subtract the loss time, you get something which we call as effective green. Okay, effective green. So yellow plus all red plus green plus yellow plus all red, total phase time minus total loss time gives you effective green. What happens during effective green? The vehicles are moving at saturation headway. During effective green time, the intervals between the vehicles is saturation headway. Okay, this is an example in which they are asking us to calculate the capacity of one approach or one lane of the intersection. Okay, using this data, so we have the total cycle length, the green time of the approach, the yellow and all red time, saturation headway, startup loss time, clearance loss time, and they're asking for capacity. There are two methods to solve this problem. We'll look at both of them. In the first method, you can use the saturation headway. So first of all, we calculate how many cycles we have in 1 hour. So how did we get 60? Each cycle takes 60 seconds. So, and we have 3,600 seconds in an hour. Okay, 60 seconds is given. Cycle length can change, but this is how you get number of cycles. Okay, so in 1 hour, then you get 60 cycles. And in each cycle, what is the effective green time? Green plus yellow plus all red minus loss time. So green was 27, yellow and all red 2, and loss times are given as 2 and 2. 2 for clearance, 2 for startup. So this will give you effective green time. Now during effective green time, we know the vehicles move at saturation headway. So how many seconds of effective green time I have in 1 hour? In one cycle, I have 27 seconds. And in 1 hour, I have 60 cycles. So total effective green time in 1 hour, 60 into 27, this much. So I have 1,620 seconds of effective green available in 1 hour. In this time, the headway between the vehicles is 2.4 seconds, the saturation value. So how many I can have in this whole time? 675 vehicles. Okay, so this is using the saturation headway. Then we can use saturation flow rate as well. So first of all, I calculate the amount of cycle length, which is effective green. So effective green is 27, same, divided by cycle length, which is 60. So 0.45 of the cycle length, there's effective green. Now, what is my saturation headway? Saturation flow rate. So 3,600 divided by interval between the vehicles, 1,500. If the whole cycle was effective green, I will have a flow of 1,500. Okay, as I told you, saturation headway doesn't take into account red and loss times and so on. So this is with the whole cycle of green, but I don't have whole cycle green. I have 0.545 of the cycle as green. So I will achieve 0.45 of this flow, okay, which is again 675 vehicles per hour. So this is how we get the capacity using saturation headway and saturation flow rate. One note about the loss time. So I said we have two loss times. L1 is startup and L2 is clearance. L1 happens when signal becomes green. So the extra headway which is taken by the first 3-4 vehicles in passing the stop line when the signal has just become green. And L2, the clearance loss time, which happens when the signal has just become red, the all red time. So L1 is start of the phase, L2 end of the phase. Okay, so these are the two loss times we have. So this is it.